Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module MOS memory devices from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the volatile memories, including dynamic, MOS, RAM, and Cmos inverter. Secondly, we will discuss about the non-volatile memories, including metal, insulator, oxide, semiconductor, MOS device. Thirdly, we will also discuss about the floating gate avalanche injection MOS device, famous. So students, let us start with a basic introduction about the module. NMOS. It's a memory device. P-channel are the memories which can store digital information or the data in terms of bits or binary digits. For large memories, random access memory RAM organization is preferred, and this is volatile memory. Now what is RAM? RAM memory cells, they are organized in a matrix form and can be accessed in random order, independent of their physical locations, to store, write, or to retrieve, read the data. Next is SRAM, static random access memory, which can retain the stored data indefinitely. SRAM cells uses a simple bistable circuit or flip-flop to hold a data bit. Generally, there are three operational modes of the memory devices. First is hold state, where the bit is stored in the cell for future usage. Next is write, where the state 0 or 1 is fed to the cell for storage. And finally, the read state, where the stored bit is transmitted to the outside world. Next is SRAM cells, which consist of 4 enhancement mode MOSFETs and 2 depletion mode MOSFETs, 6T cell. The depletion mode MOSFETs, they can be replaced by resistors formed in undoped polysilicon to minimize the power consumption and high packing density 4T cell. Volatile memories. Main type of volatile memory is static MOS RAM, where data remains stored as long as the power is maintained. So this figure below explains the operation of static MOS RAM circuit using MOSFETs. Now here, the two MOSFETs, that is Q1 to Q4, forms the bistable flip-flop, while Q5 to Q8 forms the gating network through which nodes N1 and N2 are connected to 0-bit and 1-bit lines respectively. So let us first discuss about the hold state. Q5 to Q6 or Q7 to Q8 forms the AND gates, to which XY address drives are applied for the selection of storage cell. For linear selection, remove Q6 and Q8 and X address represents the word line. In quiescent state, both X and Y lines are at zero potential, isolating storage flip-flops from the bit lines. Let us consider Q2 be on and Q1 be off, which is implying N1 equal to VDD and N2 equal to 0. Read state. To read the cell, both X and Y address lines, they are pulsed. Negative for P channel and positive for N channel, turning the gating by Q5 to Q6 on. Current will flow into the 1-bit line which is kept at the voltage, that is VDS, through Q7, Q8 and Q9. No current flows through 0-bit line which is kept at VDS since Q4 is off, and your V1, that is your N1, is equal to VDS. So the state of the storage cell is thus determined by detecting on which bit line the sense current flows. Next is the write state. To write 1 into the cell, pulse the X and the Y lines and make 1-bit line to 0. Since 1-bit line is pulsed from VDS to 0, we desire to write 1 in the cell. However, cell is already in 1 state and no change occurs since Q2 is already on. If 0-bit is pulsed from VDS to 0, N1 equal to 0, which implies Q2 is off and Q1 is on through regenerative process of the flip-flop. Thus, cell changes the state and we have the written logic 0. Note the typical cycle time is approximately 500 nanosecond to 1 microsecond. Dynamic MOS RAM or DRAM. Instead of using 8 MOS cell, it is possible to use a simpler 1 MOS storage cell in which information is stored on the parasitic gate to substrate capacitance. Thus, at the expense of requiring a refresh operation to replenish the charge leaking of the storing capacitance, we achieve far greater density of storage cells on the same chip area. For example, Intel 1103 is MOS LSI RAM 1024-bit memory and is organized by 1024 word by 1-bit array. Refreshing of all bits is required every 2 milliseconds and cycle time is about 580 nanoseconds. Reduced cost per bit makes DRAM attractive for large read-write memory size applications. DRAMs are slower than SRAMs and require more peripheral circuitry. So here a cell is controlled by word line and a single bit line provides input-output path to the cell. Storage mechanism is based on the content of temporary charge retention on capacitor. This figure shows the circuitry of 1T DRAM cell, where the stored charge in the capacitor is Qs equal to Cs Vs. So with Vs equal to 0, it implies Qs equal to 0, which is the logic 0. When Vs is positive, it implies Qx equal to Qmax. This is logic 1. Let us discuss now the right operation for it. Let the word line equal to plus VDD, which means the transistor is on. Now if we apply input Vd to the bit line, so the input data voltage Vd controls the current to from Cs. If Vd equal to 0, it implies Vs equal to 0 across Cs. It implies Qs equal to 0. This is logic 0. So if Vd equal to VDD implies Vx equal to Vmax equal to VDD minus Vt. That is, voltage on the gate reduces transmitted signal by Vt. This implies Qs equal to Qmax equal to Cs multiplied by VDD minus Vt, which is a logic 1. Let us discuss now about a read state. Now if a word line is equal to VDD, then read Qs using bit line. So charge moves from Cs to C bit, including line capacitance and other parasitic contributions such as input capacitance and sense amplifier. Charge sharing situation is QSI equal to CS Vs for logic 1. So current flows from Cs to C bit continues until Vf equal to Vs prime, and the charge is redistributed as QSF equal to CS Vs prime plus C bit Vf equal to CS Vf plus C bit Ve, since Vs prime equal to Vf. So conservation law implies that initial QSI must be equal to final QSF, which implies Vf equal to CS Vs by Cs plus C bit. This implies Vf is less than Vs for a stored logic 1. In practical, Vf is reduced to few tenths of a volt, so a design of sense amplifier is crucial. So consider a DRAM cell with Cs equal to 50 picofarad. Bit line capacitance is C bit equal to 8 Cs. Let the maximum voltage of Vs equal to Vmax equal to 2.5 volts on Cs. So the final output voltage during logic 1 read operation is Vf equal to Cs Vs by Cs plus C bit. So putting the value of Cs over here, we get and putting the value of Vs over here, we'll get this equal to 278 millivolts. Similarly, stored logic 0 resulted in Vf equal to 0 volts for Vs equal to 0 volts. Hence, the sense amplifier must be able to distinguish between 0 to 0.8 volts to determine the value of the stored bit. Hold state achieved by turning off the off transistor with the word line equal to 0 volts. So logic 1 implies Vs equal to Vmax on Cs, implying a leakage current IL flowing away from Cs. So IL equal to minus dQs by dt equal to minus Cs dVs by dt. Since Qs equal to Cs Vs, that is current removed charge from Cs, implying Vs decreases. Now this is shown graphically in this figure. Let us now discuss about the hold retention time. It is the longest time that the cell can maintain a logic 1, that is V0 in the range Vmax to V1. If we assume IL as the constant, then IL equal to minus Cs multiplied by delta Vs by delta T implies the hold time equal to Th equal to the modulus of delta T equal to Cs delta Vs by IL. Hence, the hold time increases by using large Cs and minimizing the leakage current. Students, let us consider an example. Now, if IL equal to 1 nanoampere and Cs equal to 50 picofarad and delta Vs equal to 1 volts and the hold time is Th equal to 0.5 microseconds, then memory cells must be able to hold the data till the power is applied. So, in order to overcome the leakage problem, DRAM arrays uses a refresh operation where the data is periodically read from every cell, amplified and then rewritten. So the cycle must be performed on every cell in the array with a minimum refresh frequency of about 1 by 2 Th. Complementary MOS or Cmos inverter. The combination of PMOS and NMOS in enhancement modes forms a Cmos inverter. Drains are connected together at the output. Input is a common gate. So this figure shows the schematic and the circuit of a Cmos inverter. Now here VTP is less than 0, that is between minus 0.5 to minus 1 volts. VTN is greater than 0, 0.5 to 1 volts. When input Vi equal to 0, PMOS is on and NMOS is off. Since Vi or Vg is less than Vtn, gate of PMOS is at minus VDD with respect to the source and substrate is more negative than VTP. Now when Vi is equal to plus VDD, PMOS is off since Vi or Vg is greater than VTP and NMOS is on. Since Vi or Vg is greater than Vtn, which implies Vo is equal to 0 volts, that is the logic 0, and thus the circuit act as the inverter. Unique feature. In either logic state, one device MOS in the series form plus Vd to ground is off, that is non-conductive. The current flows in either steady state is small leakage current, and only when both the devices are on during switching, it does a significant current flow through Cmos inverter. So average power dissipation, it is very small in watts. As the number of components per chip increases, power dissipation becomes a major limiting factor. So low power consumption is the most attractive feature of Cmos. However, processing of Cmos demands double steps in comparison to NMOS. So there is a trade-off between the complexity of processing and low power consumption. Stacked transistor approach. Now stack a p-channel device on the top of the n-channel device. The two can share a common gate electrode. This structure can result in a very dense static and dynamic RAM cells because it eliminates the conventional device isolation problems. So a pair of these devices forms a static memory cell that resembles the static RAM. Let us now discuss about the non-volatile memory. The information once written remains valid when the power is removed from the device. So when the gate electrode of a conventional MOSFET is modified so that the electrode of a conventional MOSFET, and here the permanent charge storage inside the gate is possible, the new structure becomes a non-volatile memory device. And this includes the EAROM, that is electrically alterable ROM, EEPROM, erasable programmable ROM, NVRAM, non-volatile RAM. So two groups of non-volatile memory devices are: number 1, dual dielectric metal insulator oxide semiconductor MOS devices. Number 2, floating gate avalanche injection MOS famous devices. In both the devices, charges are injected from the silicon across the first insulator and stored in the floating gate famous or at the insulator oxide interface of MOS devices. The stored charge gives rise to a threshold voltage shift and device is at a higher threshold voltage stage. For a well-designed memory device, the charge retention time is more than 100 years. To erase the stored charge and return the device to a lower threshold voltage stage, a gate voltage or other means can be used. Let us now discuss about the MOS, that is metal insulator oxide semiconductor device. Double dielectric layer on silicon substrate it consists of. Now here the charge is stored at the interface of two dielectrics. Among several kinds of MOS memory devices, the MOS metal Si3N4 SiO2 Si device is the most popular, and other insulators can be used, that is Al2O3, Ta2O5 and TiO2, etc. So here SiO2 in conventional MOSFET is replaced by double dielectric. So let us first discuss the right operation. So if we apply sufficient high voltage 30 volts pulse to the gate, high electric field is created in the oxide. Electrons from the conduction band of silicon tunnel into the traps located at SiO2 Si3N4 interface. So the negative charge is trapped at the interface and gives a change in the Vt of transistor. Upon the removal of pulse, that is Vg, the trapped electrons cannot flow back to silicon and information, that is change in Vt0, cannot be retained for a long period of more than a year. To switch the device back to the low Vt state, a negative pulse is applied to the gate. So the reversal of polarity causes the electron tunneling from the interface traps into the silicon. With sufficient large negative voltage, device can regain its original state or if desired. That is, there is a complete reversal of Vt. So typical switching speed during write and erase operation is 10 microseconds and increases or time decreases as SiO2 thickness decreases and trap density increases. So to increase the trap density, metal ions are implanted into SiO2. Floating gate device. Let us discuss about the floating gate avalanche injection MOS device famous. It consists of the heavily doped polysilicon layer which is inserted between the two SiO2 layers and is completely isolated from the silicon substrate as shown in this figure. So here D1 is approximately 0.1 micron and D2 is very much greater than D1. So no shorting path exists between the floating gate and the substrate. Let us now discuss how does this device write. To charge the floating gate of the device, a voltage sufficiently large to cause the avalanche breakdown of drain substrate junction is applied to the drain. So, a large number of electron hole pairs are generated in the junction depletion region by avalanche multiplication. Some electrons acquire sufficient energy to surmount the Si-SiO2 energy barrier and injected from drain region into the SiO2. These electrons drifted by the induced electric field in SiO2 by capacitive towards polysilicon gate. This injection process is called as the avalanche injection. So floating gate accumulates the negative charge, which is a function of the amplitude and duration of Vd. After the removal of Vd, charge injection is stopped, but the negative charge on floating gate is retained for several years. Since no discharge path is available for the accumulated electrons, negative charge on floating gate is normally off and the charged gate is on. The presence or the absence of charge on the floating gate can be sensed by measuring the conductance between source and drain region. Let us discuss about the erase option. This cannot be performed electrically since gate is not accessible electrically. So initial equilibrium condition, that is no charge on floating gate, can be restored by exposing the device to UV or X-ray for few minutes. So here the charge is removed by electrical means, which is possible if a second polysilicon gate is used on the top of SiO2 layer. By application of a large negative voltage to external gate, the stored charge can be removed and device can be brought back to its initial state of no charge at the floating gate. This device is Cmos memory, stacked gate avalanche control injection MOS with double level polysilicon gates. External control gate makes electrical erasing possible and improves the writing efficiency. So students, let us summarize what we have learnt in this module. Firstly, we discussed about the volatile memories, including the dynamic MOS RAM and Cmos inverter. Secondly, we also discussed about the non-volatile memories, including metal insulator oxide semiconductor, that is a MOS device. Lastly, the floating gate avalanche injection MOS device, or the famous, is also discussed in this module. Thank you.